Okay, so in this section, we're going to prove a very quick result about what happens when the derivative of a function is strictly positive or negative, or weakly positive or negative, which results in strictly or weakly increasing or decreasing functions, as the case may be. So let's just recall a function f is strictly increasing on S, let's say on a set, right? If for all x less than y in S, we have f of x is strictly less than f of y. Weakly increasing if f of x is less than or equal to f of y for under these conditions. Strictly decreasing on S if for all x less than y in S, we have f of x is greater than f of y, and weakly decreasing if f of x is greater than or equal to f of y under these conditions, right? So that's increasing and decreasing. So now we have another corollary. So this is 29.7. Another corollary of the mean value theorem, which is, so let f be differentiable on AB. Then, so if f prime of x is greater than 0 for all x in AB, then f is strictly increasing on AB if f prime of x is greater than or equal to 0 for all x in AB, then f is weakly increasing on AB if f prime of x is less than 0 for all x in AB, then f is strictly decreasing on AB if f prime of x is less than or equal to 0 for all x in AB, then f is weakly decreasing on AB. So, again, facts that you're probably familiar with, but now we're sort of proving them in a very general and rigorous way. So let's just prove the first of these. So because actually all the proofs are like extremely similar, and 3 of them are exercises. I don't remember if I assigned any of them, but either way, it would be good practice for you to try to think about how you would adapt this argument to the other 3. So let's just prove the first one. So we're going to suppose f prime of x is greater than 0 for all x in AB. So now let x1, x1 and x2 are 2 points with x1 less than x2. Then the mean value theorem for f on this interval tells us there exists a some x, I guess, in the open interval x1, x2, such that f prime of x equals f of x2 minus f of x1 over x2 minus x1. So f of x2 minus f of x1 over x2 minus x1 is greater than 0, which means that f of x2 minus f of x1 is greater than 0, right? Which is saying that, so that shows that f is strictly increasing, right? And this is because x2 minus x1 is positive, so f of x2 minus f of x1 also has to be positive. So, this is very simple. Again, you can see this is actually another example of, this is another example of the following reasoning. If P is true, P is some property or statement or something about f prime on AB, then P is true about f of x2 minus f of x1 over x2 minus x1 for all x1 less than x2 in AB, right? So yeah, this kind of reasoning can take you pretty far, I'll say. All right. So yeah, that's it for this video. And then in the next one, we'll do the intermediate value theorem for derivatives, which is kind of interesting because, again, remember, so derivatives do not have to be continuous, okay? So the fact that they satisfy the intermediate value theorem is, it does not follow just from continuity, it's something else. It's a different property on its own, okay? All right, anyway, so yeah, that's all for this video. See you in the next one.